Looks so rested and sort of springy. It's great. Hope you all had a good break. Sorry about the midterm. No, not really. It was. I'm glad you got to complete the midterm before spring break, so you didn't have that hanging over your head. We'll return those today. And overall, I thought people did about as I was predicting. The average, the mean on the midterm was 68, and the standard deviation is 15. So think of 68 plus or minus 15 as kind of the spread of grades. And by the way, out of 100 possible points, the highest score was 100. And that individual also happened to get all 6 extra credit points. So it was a solvable midterm, I'm happy to say. And that wasn't one of the TAs or me taking that. That was one of you. I think what we may do is maybe in recitation this week, maybe we can go over a few of the midterm questions that were most exciting or most contested among you in terms of their answers. But overall, I thought it was okay. And I'm sure by the time the final rolls around, you'll know even more. So it was good. Let's see. So today, what I want to do is give a little bit shorter lecture than normal, so that we can also, in terms of technical stuff, but also leave a little bit of time to talk about the projects. So as you know, in the course, the second half of the course will have many, many, many fewer homework assignments of the type that we had in the first half. Like maybe we'll have 1 or 2 short ones. And then primarily, your outside of class time will be, of course, studying the material, but doing a project. And so I want to spend some time talking about that today, too. OK, so you'll probably recall that before the midterm, we were talking about computational learning theory. And in particular, we were talking about these kinds of questions. The fundamental questions of machine learning, really. How does a learner's performance, that is the accuracy with which it can approximate the target function that it's trying to learn, how does that accuracy depend on things like the number of training examples it sees, the complexity of the hypotheses that it considers, and so forth. And we talked about really the key result in the field, which is this result on probably, approximately correct learning, PAC learning. And today what I want to do is just talk about another kind of different way of theoretically characterizing learning. So instead of asking the question, how does the probability that our learner will output a hypothesis with true error epsilon, how does that depend on the number of training examples? A different kind of question we could ask is how, if we have a learner that, let's say a consistent learner, for starters, consistent learner that is one that finds a hypothesis that perfectly fits the training examples, if possible. The mistake-bound question is, how many mistakes will a learner make on the way to getting the right answer? It's kind of an interesting question. If you think about it, if you think about a spam filter, for example, a learning spam filter, this would be equal to the question of how many mails would it misclassify as spam or not before it converges to the correct spam filter, if there were a consistent spam filter, right? Or so you can imagine lots of reasons why, especially if we're looking at what people will call online learning, that is, learners that have to train on the job, so to speak. They have to make a prediction as they're going, and then they get some feedback. They have to make another prediction on the next example, then they get some feedback. So a spam filter that you're using and correcting would be such an example. Or some kind of diagnosis, medical diagnosis classifier that was going to look at patient symptoms and say, yes or no, it's a good idea to give them this particular antibiotic to treat their problem. If we imagine a learner like that that's getting new patients coming in all the time and having to make a prediction, and then later we find out whether that therapy worked well for this patient or not, so then it gets the correct label, then it's a very reasonable goal to ask to try to minimize the number of mistakes that the learner makes along the way to learning. And that would be sometimes a more important constraint than minimizing the total number of examples that it looks at. Okay? So you can see why this is an interesting question. And also it turns out by looking at this question, we'll kind of get a different angle at looking at some of these fundamental insights into learning and how it really works. So this is the question for today. So basically, this problem setting is the same as the PAC setting. That is, we're going to assume that you have a kind of online learner that's being given a sequence of training examples. Each member of the sequence is generated by drawing some random instance, a patient or an email to be classified, from some underlying distribution, which is our P of x. And then the learner must classify that example. Then the trainer gives it a label, and we're asking this question about, can we bound the number of mistakes? Okay, so I want to just start with a very simple algorithm and ask you to come up with a mistake bound. So the simple algorithm is this. Let's suppose, as usual, or as we've commonly done in the past, we're going to assume each example is just a vector of, let's say, Boolean features. So those will be our examples, just a vector of n Boolean features. And let's assume each hypothesis is a conjunction of Boolean literals. And by that I mean a constraint on any subset of these. So for example, I'll say e.g. Our hypothesis could be that x sub 2 must be 1 and x sub 7 must be 0. Okay. Actually, to follow the notation that we're using down below on the same slide, I could say, well, here's some literal, I'll call this literal 2 that's requiring the x2 be 1, and I'll call this not x7 must be 1. Okay? So I'm just defining that because I see the slide below uses this other notation. But the idea is simple, right? Every hypothesis is just a conjunction of constraints on the values of the different features. And if that is satisfied, then we're going to say y equals 1. Right? And here again, we're assuming the label we're trying to predict is also Boolean. Okay? So simple learning problem. The examples are just feature vectors of Boolean features. We're trying to predict a 0, 1 valued function. And the hypotheses we're considering are these simple rules of the form either constraining an arbitrary x sub I to be 1, as here, or constraining it to be not 1. Okay? All right. So now think about the following simple, pretty cool algorithm this is a consistent learner for this hypothesis space. When I say consistent learner, again, I just mean that we're assuming there is a hypothesis that perfectly fits the training examples. And this one will, in fact, find the most specific one. Most specific in the sense that what's over here is as complete as possible, as specific as possible. Okay, so here's the algorithm. First, we initialize our hypothesis. This algorithm is just going to make up an initial hypothesis and keep modifying it every time it makes a mistake. The initial hypothesis is the ridiculously impossible, well, the initial hypothesis essentially says that y is never 1 because it says L1 and not L1, meaning x1 must be 1 and x1 must not be 1, and L2 and not L2, etc. So that's the most specific hypothesis we could make up. Obviously, that hypothesis will label every instance 0. Okay, so now for each, now the algorithm, you should just wait. Here comes the training example. If it's a negative example, ignore it. If it's a positive example, remove from H any literal that's not satisfied by this positive example. So here comes a positive example. Suppose it says L1, x1 equals 1, and L2, x2 equals 1, and not L3, x3 equals 0, etc. Then when we see that first example, we end up crossing out the particular literals that don't match the positive example that we see. Right? So now it's a little bit more general hypothesis. In fact, after we see the first positive example, and we'll end up crossing out half of these terms. And after the first positive example, we'll have a hypothesis that labels that positive example positive, y equals 1. It'll label everything else negative. Okay, now the second one comes in, we do the same thing. So just every time we see a positive example, if it's not predicted to be positive because our hypothesis is too specific, we remove the offending literals from the hypothesis so that it generalizes just enough to cover this new positive example that comes in. Okay, so I'll call this algorithm FIND-S, shorthand for find the most specific hypothesis that fits the data. Okay. How many mistakes will this make? N plus 1. Okay, so we have a vote for N plus 1.
So is it a valid hypothesis that is the conjunction of nothing?
Is it what?
Is it a valid hypothesis that the conjunction of nothing?
The conjunction of nothing is also a valid hypothesis. That would say every example is positive. So an empty conjunction would, yeah. So the null set of crossing out all the literals would also be legit. So you agree with N plus 1? Okay, so I guess I like the N plus 1 as a bound. What I really should say is the number is less than or equal to N plus 1. Right? Okay, so and the reason, of course, is this. How many literals are in the first hypothesis? 2 times n. How many get removed the first time the first positive example comes in? Half of them, right. So we start with 2n literals. When we make first mistake, which is when that first positive example comes in, it will be a mistake because this thing is going to label it negative. It's going to say y equals 0. So when we see that first positive example, we'll remove n literals out of those 2n. Half of them will go away, right? And now, when we see the second, the next, now other examples come in, positives and negatives. If they're negatives, well, let's come back to negatives. If they're positive and we make a mistake, then we're going to have to remove some more literals. And in the worst case, well, in the extreme case, we'll just have to remove one. Right? So for the second mistake, we'll remove at least one. Right? One or more literals, because this thing was too specific. Maybe it just differed by one feature, so we'll have to remove that one. Okay, so in order, and we can't remove more than 2 n literals. There are only 2 n literals to begin with. We removed half of them on the first thing. And then if we make k mistakes, so essentially this is going to be the first time we will definitely remove n literals. On all other mistakes, we'll remove at least 1 literal. And so we're going to have to make, so the number of mistakes that we make have to remove all the literals. So it has to be equal to n plus that first one. If we make that many mistakes, we get down to the empty set of literals, which means that our hypothesis will predict everything as the label one. Okay. So the argument, the form of the argument here is very simple. What we said is, every time we make a mistake, there's a structural change that we're going to make to the hypothesis, and it involves subtracting one of these literals from it. And there are only a certain number to begin with, so by the time we're done, we can't make more mistakes than there were opportunities to remove literals. Okay. So therefore, the most mistakes it can make is n plus 1. Okay, does that make sense? Good. Okay, so you get the idea. There's a simple mistake bound for a particular learning algorithm using a particular hypothesis space. And in fact, one thing that's kind of interesting is for the PAC learning results that we talked about, you'll notice that most of our results were not about a particular learning algorithm. They were about any consistent learner that uses this hypothesis space, or in fact, any agnostic learner that used that hypothesis space. It was really about any learner that finds the best hypothesis within this hypothesis space for the PAC results that we talked about. But when it comes to the mistake-bound results, most of these are actually specific to an individual learning algorithm. And you can kind of see why. The form of the proof that we just did here, really had to rely on knowing how the algorithm was going to respond to a mistake. And so it'll turn out that most of the mistake bounds are tied to individual algorithms. Okay, so there's a simple example. Now, here's an interesting case. Here's an algorithm I'll call the halving algorithm. We almost alluded to this before the midterm, but let me define it this way. I'm going to define the version space. Remember we talked about epsilon exhausting the version space when we did our PAC learning results. And you'll recall the version space with respect to some hypothesis space and some set of training data is just the set of all the hypotheses in H that happen to perfectly label all the training examples. Right? That's what we said the version space was. So before we see any training examples, it would make sense that the version space is just the whole hypothesis space. Now, the candidate elimination algorithm, or the halving algorithm, I'll use either name, explicit is an algorithm that, let's not worry about computational tractability. But in principle, imagine an algorithm that just keeps track of the whole version space. So it starts out by initializing the version space to the entire hypothesis space. And then step 2, every time a new training example comes in, it throws out any hypothesis in the version space that happens to not correctly label that new example. And so then it waits. Here comes another training example. Oh, all these hypotheses in the version space label that new incorrectly. Leave it alone. Here comes another example. Might be positive, might be negative. Oh, this hypothesis here doesn't label it correctly, so we modify the version space to remove that hypothesis. So essentially the algorithm is start by considering all the hypotheses. One by one as you get training examples, throw away the hypotheses that are not perfectly consistent with this new example. So that at any given point, we stop, we have the remaining hypotheses in the version space are just all the ones that are consistent with every example we've seen so far. Okay, so it doesn't sound all that tractable, but in principle, you can easily imagine as a thought experiment running this algorithm. Okay, so now we see some number of training examples, and maybe we start with the version space is equal to H, but then we start seeing some examples, and after a while we have some version space left, which is the subset of H. Then we have a new example to classify. Let's pull up our big picture here. Some new X to classify after we've seen a bunch of training examples. We have some new X to classify. What we'll do is we'll classify that new example by just using a majority vote of all the hypotheses that are in the version space. So if there are 7,000 hypotheses that were consistent with all the training examples we've seen, we'll have 7,000 different voters on this new example. Some of them will label this new example positive, some will label it negative. We'll take a vote. It seems reasonable, right? It's kind of a least commitment kind of learning algorithm. It says, I'm not going to diss any hypothesis that done perfectly on the training examples. I'll let them all in. They can vote. Okay. So let me ask you. Actually, let's start with the second question. If we have such an algorithm, and you want to be kind to the algorithm to minimize the number of mistakes to it that it will make along the way. And its mistakes are when this majority of the current version space votes in the wrong direction. That's a mistake, right? So if you want to present training examples to teach it some hypothesis that's in its hypothesis space, what's the minimum number of mistakes you can get it to make before zeroing in on just exactly the right hypothesis?
So what if in the majority voting there, the positive votes and negative votes are equal numbers?
Yeah, if it's a tie, what are we going to do about a tie? Well, in the spirit of best case, let's assume whenever there's a tie, it flips a coin and it gets it right.
So I mean, in that case, it doesn't make a mistake. Luckily.
Okay, so then the suggestion here is 0 mistakes. Is that right? So what could happen? Well, let's think about it. Suppose we start with a version space equal to all the hypotheses. Here comes a training example, and let's say the majority of the hypotheses label it correctly, but a minority get it wrong. Then that's fine, because the majority vote is going to be correct. We don't charge it a mistake. It's okay internally, it had some quarreling, but it came out with the right answer. No mistake. And the version space shrinks. The minority who were wrong, they got eliminated.
But the learning algorithm's hypothesis space isn't the hypothesis space that little, I mean, it's not the same as big A. It's like subsets of A.
That's right.
So which H do you
Yeah, that's a good point. So you're saying we're a little bit underspecified here because H could be the power set of X, right? It could be that every subset of X, every teachable concept, every subset of X could be represented by H or not. Yeah. You've put me into a hard spot, but of course I want to be generous and say yes, H, let's consider the case where H represents the power set of X, where every teachable thing can be expressed in H. There's a little bit of a technical problem with that. When the first example comes in, what will the vote be? It's going to be a tie vote. Because the power set of the instances can be represented by H, therefore exactly half of the members of H are going to include this new instance and half will exclude it. And so the first vote will be a tie vote, right? Okay, now whoever's right or wrong, half of those guys go away. Second instance comes in. What's the vote? Tie vote. Right. It's ties all the way down. So that's kind of unfortunate, but insightful. So I'm glad you brought this up, even though it makes my question sound stupid. Because basically what we're saying is we have a bunch of tie votes.
And then we flip a coin and it makes it right every time, so therefore 0.
Right, which is why I wanted to be an optimist. So if we say, well, it's going to be lucky, and suppose it's not lucky, suppose it's just averagely lucky. It gets half of those ties correct and half incorrect. That's a good, okay, so what's the expected number of mistakes in that case? That's a good question.
So then there's no like best case or worst case in the original meaning that you intended.
Well, there actually is. Actually, we could consider other H's too, but let's stay with this. So let's suppose H is fully expressive, can represent every possible teachable concept. So the first example comes in, and it's a tie vote, as we discussed. And let's say every time there's a tie vote, there's a 50% chance of guessing the right answer anyway. You know, it just flips a coin whenever there's a tie. And it gets half of those right. So now what's the expected number of mistakes before the version space converges to just the one remaining hypothesis?
Half times log base
1/2 times log base 2 of H. I guess you mean number of hypotheses in H. Good. You want to say why? I like that answer.
Well, there's going to be log base 2 of H number of times of flipping points, because that's how many steps it takes to get to one single hypothesis, and every single time there's a half chance of hitting it.
Perfect. So if you didn't hear it in the back, what he said was correct, that they're going to be log base 2 H number of tie votes. And after you have that many, you've thrown away half of the remaining version space log base 2 H times, and at that point, there's only one hypothesis left. Right? So there are a couple ways, and then he multiplied by half because we're assuming it's going to get half of those tie votes right by chance. And the other half will be mistakes. So the number of mistakes, here is that. Okay. So here's another way of thinking about this. What's the initial size of the version space? Is H, right? And after one mistake, and now let's just consider the general case. No more assumptions about whether H is completely expressive or not. For this is going to cover every possible hypothesis space, H, that the system could conceivably use. After one mistake, If it made a mistake, that meant that the, so in that case I should say the initial version space is just the number of hypotheses in H, that's its size. After it makes one mistake, that means most of the members of the version space were wrong. Or at least half of them if it was a tie vote and we got it wrong that way. So now the size of the version space after one mistake is at most less than or equal to H times 1/2. And after K mistakes, less than or equal to what? Right? Every time we make a mistake, we just multiply the size of the version space by 1/2 or worse. Okay? And then what we're interested in is when the size of the version space equals 1. And so that means well, actually, I'm not going to draw that arrow. This means K is less than or equal to log base 2 of H. And actually, it's the floor of that. Okay, so the number of mistakes that we make, if we want this thing to be 1, then we want K to be log base 2 of H. So when we do that, it ends up being 1. Right? So there's the general case. And in our tie vote case, we gave it credit for getting half of them, the expected it to get half of them right by voting a tie and flipping a coin. So wouldn't necessarily have to suffer a mistake there. Okay? So it's kind of interesting. Basically, we can bound the number of mistakes of this voting algorithm, you can see why now it's called the halving algorithm. So every time it makes a mistake, it halves the size of the version space that remains. And after you have it, log base 2 of H number of times, there's only one thing left in it. And the only time that you'll make a mistake is if most of the things are wrong, and therefore you're going to, at least half of the things are wrong, and therefore you will have it. Okay? All right, so we're good. Okay, so now we actually, armed with that idea, there are some kind of general things we can say. So here's an interesting result. Let's let MA of C be the maximum number of mistakes made by algorithm A to learn concepts in C. These are the concepts that the teacher might try to teach. And when I say maximum, I mean the maximum over all possible concepts in C that the teacher might choose to try to teach, and over all possible training sequences. So I might try to teach a particular one, and there are lots of different sequences in which the examples could come in. So I'm interested in the worst case in a way. The maximum number of mistakes that this thing will make over all the possible sequences of examples the teacher might provide. Then we'll say the optimal mistake bound for that class of concepts is the minimum over all possible learning algorithms. Okay? So if a teacher, they're considering the class of concepts C, they're going to pick a concept, teach it, making up some sequence of X's and Y's to show the learner. And so I'm interested in the optimal mistake bound. That is, what's the best algorithm A? We have different algorithms that are trying to learn from this. Some will make more mistakes, some will make fewer. Can we bound the M sub A of C, the worst case number of mistakes, made by the best algorithm? And so let's start here. This one's easy. We know we can make the number of mistakes that the halving algorithm makes if it happens to use C as its hypothesis space. Right? And that's log base 2 of C. That's the number of mistakes it will make. Okay? So that's just from the previous slide. We just proved that the halving algorithm would make, at worst, that number of mistakes. So we know that there exists an algorithm, the one we talked about, halving algorithm, that can bound the number of mistakes to that. So we know the optimal number of mistakes that any algorithm can make is at least as good as the halving algorithm, because that's an algorithm. Maybe there's something better out there. But here's something interesting, the VC dimension back. Why is that? So what we're saying is that the optimal number of mistakes an algorithm can make in this worst case sense, MA of C, is bounded from below by the VC dimension. Now why would that be?
Just consider the set that can be shattered by C. So it's back in the picture of the previous slide.
Exactly, exactly. So we just go back to our definition of the VC dimension. That's the number of distinct instances where we can guarantee zero training error. It's the size of the largest shatterable set of instances. And so that means C, if our algorithm is going to use a hypothesis space big enough to cover C, and C has a VC dimension, has some VC dimension, let's say if its VC dimension is 5, just to make it easy to visualize, that means there's some set of 5 instances for which its hypothesis space can represent any of the 2 to the 5 possible labelings of these 5 examples. And so in the best case, even with the halving algorithm, you can see that at best it's going to have tie votes that number of times. Because if it gets this example first, it's not going to be able, well, you get the idea. It's there in the set of, it's there in the number of different ways H can split up the labelings of those points. So this is an interesting general result. And this one, in fact, of course, is about any learning algorithm. So we know that there doesn't exist a learning algorithm that can be guaranteed to make a number of mistakes smaller than the VC dimension. We know the halving algorithm gives us an upper bound. And now there's room in between there to explore different learning algorithms as we like. So I kind of like that result because it's an example of a kind of generic result, not just about a particular learning algorithm. Okay, so here's another algorithm, and this one actually starts to link us into practical algorithms. So here's an interesting algorithm for which we can get a nice mistake bound. In fact, we'll prove this one. It's called the weighted majority algorithm, and the idea is this. Suppose we have a collection of, I'll call them algorithms. A sub I denotes the ith prediction algorithm. And these could, for example, be different hypotheses in the hypothesis space, for example. And what the weighted majority algorithm does is a lot like the halving algorithm, except that the algorithms don't all get the same vote. They get a vote based on how many mistakes they've made before. So you can think of the halving algorithm that we discussed is kind of an extreme thing. You get a vote of 1 if you've made no mistakes, and you get a vote of 0 otherwise. And this is kind of a softer version of that, where essentially, if you make a mistake, your vote weight gets decreased, but it doesn't go to 0. The more mistakes you make, the more it gets decreased. Okay, so let's look at it in detail. So A sub I, let's let that denote the ith prediction algorithm, for example, the ith hypothesis in our space. And each of those will have a weight W sub I that decides how heavily its vote will count when we come to classifying a new example. So then what we'll do is initially we'll make all the algorithms have the same weight of 1. And then each time we get a new training example in, the X with its correct label, C of X, we measure essentially the vote mass for assigning Y equals 0 and the vote mass for assigning Y equals 1. And so if we go through each algorithm for each I, if the algorithm I votes 0, then we add its weight to the mass of weight voting for Y equals 0. On the other hand, if it votes for 1, then we add its weight to the mass of weight voting for Y equals 1. And then when we're all done, we just look and see which one is greater. And if there's more weight mass voting for 1, then we output the prediction that the label is in fact 1. Otherwise 0. If it's a tie, then we flip a coin. And then, furthermore, when we get our label, we update the weights by, if they're correct, we do nothing. We leave their weight alone. It's still whatever it was before, maybe 1 still, if it hasn't made any mistakes. But if it makes a mistake, we're going to multiply its weight by some number smaller than 1. For example, when beta equals 0, that's just the halving algorithm. It's like saying you made a mistake, you're out of the running. Your vote is 0 now. But we could use something else, like maybe beta equals 0.5. Whatever number we like. So now we're saying, we don't trust you as much, but we're not going to 0 you out. Okay? And this can be an interesting algorithm, even if we have a collection of learners using different learning algorithms. They could be our A sub 1, A sub 2, A sub 3. Right? There's nothing here that says this must just be hypotheses. Could be learners too. Okay, so there's the algorithm. And you can see its clear correspondence. It's a generalization of the halving algorithm that we just discussed. Now here's the interesting result. Let's look at it. It's a mistake bound on this weighted majority algorithm. And the mistake bound says, let's let D be any sequence of training examples, and A is any set of n prediction algorithms, and K be the minimum number of mistakes made by the best algorithm in A, the lowest, the one that makes the fewest mistakes. Okay, so for example, if A is my set of hypotheses, then K is the number of mistakes made by the best hypothesis that I'm considering. Then the number of mistakes made by the weighted majority algorithm is related, if we set beta to 1/2, for example, is related to K, the number of mistakes made by the best algorithm in the pool. This is actually very interesting. So it's essentially n, where n is what, the number of distinct algorithms in our pool, the number of hypotheses in the space, for example. So what this is saying is this thing that's weighting and voting these different hypotheses makes a number of mistakes that can be guaranteed to be bounded by the number of mistakes made by the best individual in the pool, even though the algorithm doesn't know in advance which one is the best. So this is kind of a bound between the best member of the set and what the weighted majority vote will provide. This is a nice kind of thing. So it means if you've got a good algorithm in there, then your weighted majority algorithm is going to benefit from that. It's not going to make the number of mistakes it will make will be bounded by the number of the made by the best one, and also with this log n term where n is the number of all the alternatives being considered. Okay, so let's prove this. It's actually an interesting thing to prove. So again, what we want to, let me copy this over. So we want to prove that this is an upper bound on the number of mistakes by the weighted majority algorithm.
So, what does the definition of K mean?
K is the minimum number of mistakes made by any algorithm in A. So we have this pool of algorithms. We'll call it A. We might think of it as all the hypotheses that we're considering, if you like. That could be an algorithm. And here are different hypotheses, let's say, or different algorithms. And this one makes 17 mistakes. This one makes 7. This one makes 4.
So that's the best case or worst case?
Minimum number of mistakes.
I mean,
Oh, you're saying is it best or worst? Before we were talking about best or worst case taken over different sequences of training examples.
There's a minimum and there's an any, so which one applies to which?
Right. In this case, it's a different setting from what we talked about before. So you notice D here is any sequence of training examples. So there's some sequence of training examples D. No matter what that is, if we count the number of mistakes made by every algorithm in our pool and find the smallest number, that is K. That is K. It's K for this sequence D. And what the guarantee here is that the weighted majority algorithm will make no more than this number of mistakes as a function of K, the number made by the best thing, for this sequence of examples D. So this is a slightly different setting than we talked about before, because before we were talking about the kind of worst case number of mistakes over all possible sequences D. And what this is saying is no matter what D is, this bound will hold.
There are two questions. So first is that even when D is given, the number of mistakes made by a given algorithm can be undetermined because there can be point collision.
Well, I don't think so. So the comment is, depending on D, the number of mistakes could be quite large. I guess that's true, but if there's a consistent learner and a consistent set of labeled examples, we can assure that's 0. But this result is more general than that. It does apply to any sequence in any situation.
You didn't answer my first question, and also there's the second question. Since there is an algorithm in this set of A that makes the minimal number of mistakes, so why don't we just shrink this set of A to contain that only one algorithm, so that n equals 1, and then you get it?
Ah, okay, good. So the question is, well, if we have a low mistake algorithm, why don't we just use it? And the answer is because we're assuming that the problem is we don't know which of these algorithms is good, if any, and we don't know that in advance. That's the learning problem. So we've got a pool of algorithms, just like if we have a pool of hypotheses. We don't know which one's the best one. We're getting data, and we're applying this weighted majority learning algorithm to reweight the different things, just like we applied the halving algorithm as a special case of this. So it's a learning setting. That's why we're doing it. Yes?
But I guess in practice, then, would you eventually throw out everything in the pool that was less effective? Like, would you train the model
That's right. So once you're, if we're applying this to a learning setting where it's our hypothesis space is the set A, then we already know that after we've made log base 2 h number of mistakes, we'll be able to know exactly which one is right, if a consistent hypothesis is possible. And if that's the case, then we might just want to say, okay, we're going to eliminate everything else. But this result is actually somewhat more general because this allows for the possibility that there's no consistent hypothesis. And so if we want to, so this is kind of the, this is literally would cover the agnostic learning setting where we don't know in advance that the correct hypothesis is even in there. In which case, probably we just want to continue to use this algorithm. Okay, so let's do our proof here. And so let me do this way. I'm going to say let M, capital M, be the number of mistakes made by the weighted majority algorithm. The weighted majority algorithm. And as we said before, little k is the number of mistakes made by the best A sub I in A. Okay. So weighted majority is considering the set of algorithms A, and k is the number of mistakes made by the best algorithm in there, smallest possible number of mistakes. So now what we're trying to do is we're trying to relate M to k. We're trying to bound the number of mistakes M that our weighted majority algorithm will make in terms of k. So the obvious way to do this is to say, well, what is, let me ask you, what is the final weight of algorithm A sub I? And let's go back here and notice that our algorithm, each algorithm began with a weight of 1. And then every time it makes a mistake, its weight is decreased by beta, which in this theorem we're going to assume is 0.5. Okay, so what is the final weight of algorithm A sub I? Right. Just beta. Well, it's 1/2. We're going to multiply it by 1/2 each time. That's beta. And if it makes k mistakes, then it's going to be down multiplied k times. And it started out with a weight of 1. So that's its final weight. Okay, so now let me ask, what is the final I'll make that a J. What's the final sum of weights for the entire collection of algorithm, collection of A sub I's?
F goes up to the n times the number where the number of algorithms.
Right, close. So that's pretty close. Not quite. So let's think about it this way. So what is the initial? Let me call this quantity. Let's use capital W to be the sum of all the weights. So what's initial value for that? Yeah, that's right. So let's say n. So there are n algorithms. Okay, so initially it's n. So now if the weighted majority makes a mistake after the first mistake, what's the weight mass after the first mistake? So let's see. A mistake happens if the majority of the weight mass votes incorrectly. Okay, initially that's easy. All the weights are 1. At least 1/2 W of the weight mass voted incorrectly. Okay, that 1/2 of W is now going to be multiplied by beta, 1/2. And so it's going to be reduced from being 1/2 W, or 1/2 N, to being 1/4 N, right? Now the other half, they're going to remain untouched. They weren't wrong. So their weights remain unperturbed. But this half that voted wrong, they're going to get decreased by half. So if we started with a weight of N, we're going to now have N times 3/4, right? Because this half remained intact. This other half got shrunk by being multiplied by 0.5, right? So after the first mistake, right? Now what happens after the second mistake? So now we have algorithms with different weights in the pool. But again, the only way for the weighted majority algorithm to make a mistake is for most of this weight mass to go in the wrong way. And so if that happens, that means 3/8 of N must be voting the wrong way, because right now the total weight mass is 3/4 of N. So now 3/8 at least of N must be, times N must be voting in the wrong way, and that'll get shrunk to 3/16. So basically, after K mistakes, every time we make a mistake, the total weight mass goes down to 3/4, to at most 3/4 of what it used to be. Because again, at least half of the weight mass must be wrong. That half gets compressed by half. The other half remains intact, so we get another 3/4. So every time there is a mistake, by the weighted majority algorithm, its total weight mass goes down by a factor of 3/4. If we starts with a total weight of N, weight of 1 for each of the N hypotheses, and now if we make K mistake, it's 3/4 to the Kth. And now we've just about proven it, because what else do we know? Well, it's kind of an obvious thing, but we know that the weight for algorithm I is certainly less than the sum of all the weights over all the algorithms, which includes I. And so we just said the final weight after whoops, I shouldn't have used K. K I reserved for the number of mistakes used for A. I was going to let M be the number of mistakes by the weighted majority. So let me call this mistake M. Right? Just to keep our notation straight. So we're assuming on the top line there that the weighted majority algorithm made M mistakes, and that the best algorithm made only K. Well, made K. I shouldn't say only K. I don't want to bias this. So now we know that we know this quantity, and so we have an expression. We know this inequality, and therefore we can rewrite it as that weight must be greater than or equal to 1/2 to the K. There's a line there. I'm just going to move this just so that we don't end up with slides that mislead people into thinking subscripts. So after mistake M, we have that. And so we know that weight is greater than the final weight of algorithm I, which we know up here. is, we already calculated what that would be. And so we know that that's at most 3/4 m. So that's the expression that gives us the relation. And that's the theorem. The version of the theorem that was on the other slide had some approximation to this in it, with this 2.4. But basically, what it's showing is just a rearrangement of this. So if we take both, say the log of both sides, you have k times log of this. It's less than m times log of that. And that's essentially it. So what's nice about this, you see what it's saying. It's actually kind of a surprising. First time I saw this, I was actually quite surprised you could get a result like this. But it's saying if you have a pool of hypotheses or algorithms, you don't know anything about them. They might even be, this theorem even allows for each of those algorithms to be a learning algorithm. It's learning along the way while you're presenting examples. Our proof still applies. It doesn't even, it's not even restricted to those algorithms being static hypotheses. They might themselves be learning algorithms. But in any case, we can bound the number of mistakes made by the weighted majority algorithm in terms of the number of mistakes made by the best member. Okay, so that's going to wrap up our coverage of computational learning theory. There's a lot more to say. In fact, Avram Blum, a professor in the computer science department, teaches a course on computational learning theory, so you could take a semester-long version of this if you like and learn a lot more. But I think, you know, the things that are important for you to get out of this are the basic insights from path theory and these kinds of mistake bounds as well. And just the idea that the VC dimension of a hypothesis space is a very useful way of characterizing the complexity of that set of hypotheses as it impacts the amount of training data we expect to need in order to achieve some bound on the accuracy of our learner. The mistake bound stuff gives another kind of different angle of looking at some of these questions. And so I think just understanding this set of results, I know has helped me to just kind of have a good framework for thinking about new algorithms and how they fit into this. So that's what I want to say. There's a conference in this area. You can go look at the papers are up freely downloadable on the web. If you're interested in this topic, there's plenty of ways to pursue it. So any questions, comments on this before we move on? Okay. So then let me just take 5 minutes to talk about course projects. We have, or soon will have, okay, thank you, Carl. We have on the website filled in the course projects page. And what you'll see there is that we'd like you to propose in a one-page proposal a week from Thursday your project. So you have this week and next week to talk with us all about it. You'll also see on there that there are a list of data sets that you could use if you like, on probably 10 or so ideas on that course page, web page, about data sets and ideas for what you might explore. Here's a prototypical example of a course project. So here's one that a student did in a previous semester. To me, it's kind of a prototypical example. They took an interesting data set. In this case, it happened to be text classification data. And they said, well, I'm going to develop one of the algorithms that we talked about in class and apply it to this data set. And then I'm going to do something interesting beyond that. And so what they did was they took naive Bayes They applied it to this data set. You can't do that because you just did that for homework. But they hadn't. So they did that as the first part of their two-part project. And that gave them a chance to explore some algorithm that they hadn't implemented previously. But that was kind of an off-the-shelf idea that was fairly straightforward conceptually. Try it out on some data. And then they had the second half of the project period, the next 3 weeks, to extend that in some interesting way. And what they did was they found this paper on weakening the conditional independence assumptions of naive Bayes by adding a tree-structured network among the X of i's. And so they experimented with doing that. And so for me, that's a prototypical example of a project for this course, because it's good to do it in this kind of two-part way, where part one, you're absolutely sure you're going to succeed. Because it's a matter of taking some algorithm that is well understood by you, maybe hasn't been implemented by you yet, trying it on some interesting data set, and you know you can do that. And in fact, we'll ask you in this proposal to indicate what is your midway milestone. This would be an excellent midway milestone. I'm going to take this algorithm that I understand well in this data set. I'm going to apply it to it. I'm going to report on the results. I'm going to make sure I'm not overfitting, etc. And then beyond that midway milestone, I'm going to explore some kind of interesting issue that goes a little bit more, reaches a little bit more out there. And so that's a great template for you to use as your project. I strongly recommend that. You can use your own data set if you like, provided you already have it in hand. We'll approve pretty much any proposal that you come forward with that says, I'm doing research on data where I've put little locators on people's fingers and watching them type, and I've got this time series motion of how their fingers are moving, and I'm going to try to predict how long the words are that they're typing. I don't know. If you have that data, we'll say, okay, what's your midway milestone, and what's the baseline approach you're going to try, and what are you going to do for the second part? But we'll approve it if you already have that data in hand. We will not approve it if you say, oh, and step one is I'll collect some data like that. And then the reason we won't approve that is you just don't have time to do that. You don't have time to collect data and do your project. So we want to make sure you start with the data so you can focus on the content. So basically, we'll ask you a week from Thursday to turn in these things. You can turn them in earlier if you like and get feedback sooner and get started. We will give you feedback on those. So if you think you know what you want to do, turn it in this Thursday. Don't wait till next Thursday. And you'll get feedback from us much quicker. We'll ask you to set a midway milestone. We'll ask you when that milestone comes up, which is April 12th, to turn in a midway report summarizing your progress to date. We'll ask you then to turn in a final report at the end of the semester. And we'll have a poster session at the end of the semester where you'll present a poster of your results. And we and anybody else who's interested, if you want to invite your friends, bring them. Actually, we always end up with people who aren't in the class floating through and looking at the posters. So I'm serious when I say feel free to invite your colleagues and friends too. So proposals due a week from Thursday. On April 12th, there's a midway report due. In your proposal, what you should do is indicate what your milestone is for April 12th that you're going to include in your midway report. And then final reports and posters at the end of the semester. If you want to work in pairs, that's fine. If you want to work in groups bigger than 2, my default is to discourage that, just because the group gets unwieldy if it's too big. But if you have some overwhelmingly compelling reason why this set of 3 people should do a project together, propose it. We'll listen. So I think that's it. Any questions about projects? Okay. So if you're doing research already in some area where you think you could try out machine learning on your data that you have for your research, it's a good opportunity. Okay, we also will return the midterms now.